Welcome back. You might have noticed up till now that we haven't looked at a single logarithm or exponential function, and that's because we've saved it all for this chapter. And that's also because we want to start off with presenting another way of defining a logarithm. So when you learned logarithms back in the day, more than likely it was that you had learned exponential functions first, and then you learned that logarithms were the inverse of an exponential function. Here, though, we're going to start off with a rather different definition of a logarithm. In fact, we're not even defining all the logarithms yet, specifically just natural logarithm of x, and we're going to define it as this definite integral, which is going to be the definite integral from 1 to x of 1 over t dt. Of course, 1 over t, that's above the x-axis, so we could interpret this as an area. So in other words, the natural log of x would be the area going from 1 up to whatever x is, and would be the area under that curve. So we're going to look at that a little bit and talk about why this is actually a reasonable definition for natural log of x. Specifically, that this definite integral has all the same properties that natural log of x does, so it is a good enough definition for it. So first things first, we get the derivative right away. So that's kind of one nice reason to define our natural log of x as this definite integral, and that's because with fundamental theorem of calculus, if you were taking the derivative of natural log of x, well, I would be taking the derivative of this definite integral. And by fundamental theorem of calculus part 2, I would know that that definite integral's derivative would be 1 over x. So automatically, once we've defined our natural log as a definite integral, we also immediately know its derivative, 1 over x. Now, like I say, we are defining our natural log as this definite integral. Historically, it was more the case that they were exploring the area under the curve of 1 over x, and noticed that the areas that they would calculate that they followed that sort of property that the logarithms have. So for example, if you were looking for the area from 1 up to 6, that was the area from 1 up to 2 plus the area from 1 up to 3, because 2 times 3 is 6. And they noticed that, and then they realized that the area under the curve actually had all the other properties that logarithms did. So that's what we're going to do as well. We're going to start off with this as our basic definition for natural log, and we're going to show that it follows all the regular log properties that we would expect it to follow. So some of the basic properties for natural logs, I mean, we know that its domain is positive numbers and its range is all real numbers. We know that the function is continuous, increasing, one-to-one, concave downward. And we know this intuitively because we know what the graph of natural log looks like, because we've already been through pre-calculus, and we can just say, oh yeah, because we know what it looks like, it must have that kind of a shape. But right now, at this point in the course, we have not actually figured out what the graph of natural log of x looks like. So I'm going to have to ask us all to sort of clear that from our memories temporarily and remind ourselves that right now the only thing that we know about natural log is it is defined as that definite integral. And I want to show just based on that definite integral definition, that I can still conclude all of these things. The domain part is a pretty easy one, and that one is just straight up because we have our definite integral from going from 1 to x of 1 over t dt, and 1 over t is discontinuous at 0. So if we are starting our definite integral at 1, we can't go to the left of 0 because that would cross over our discontinuity. So whatever x is, it needs to be to the right of 0. And that's a good enough explanation for the domain. For the range, I'm going to be skipping over that part of the proof. It's not hard enough to do. So once we show that our function is increasing in one-to-one, then to show that the range is all the real numbers, we just have to show that as we're getting close to 0, the y values for natural log are becoming negative infinite. And as we go further to the right, the y values are becoming positive infinite. And since we're increasing in one-to-one, then we must be going through all the real numbers from negative infinity to positive infinity, essentially kind of using intermediate value theorem to justify things. But I'm going to do the proof of the other two parts. The continuity increasing in 1-to-1 of our natural log function, and then concavity, it being concave down for the whole domain. So the first part is actually pretty straightforward, at least for the first two. Being continuous and increasing, I actually get that right away from the derivative. And that's because I know that if f is natural log of x, by our definition, then the derivative is 1 over x. And the one thing that I know is that this derivative is good for any x greater than 0. And that's because, of course, for natural log of x, that's only defined for x is greater than 0. That's coming from our domain, knowing that it's all positive numbers. So, hooray, good for us. We took a derivative, and here I'm going to flash back to chapter 2. For a function to be differentiable, it has to be continuous. So, since f prime exists, for x being greater than 0, then that means f must have been continuous for x greater than 0. So continuity, we've squared that right away. We have continuity because we were able to take the derivative. And of course, the reason we knew that we were able to take the derivative was because we defined our function f of x as a definite integral. And thank you, fundamental theorem of calculus, for that one. Okay, the next part of part 2 is that the function is increasing, and that also comes from the derivative. Because we know that the derivative, 1 over x, is always greater than 0 if x is bigger than 0, so therefore f is increasing. So not too shabby. We've managed to show basically just by knowing that the derivative exists and what it is, that the function is continuous and increasing. 1-to-1 only takes a little bit of extra work. So remember that for showing that a function is 1-to-1, we would need to show that different inputs give you different outputs. So remember that that's our definition from 1-to-1 back in pre-calculus days. That was the reason why something like 1 over 1 y equals x cubed was 1-to-1, because if you pick two different x values, you will get two different y values, versus something like y equals x squared. It wasn't 1-to-1 because you could pick two different x values and get the same y value. So here, to show that our function is 1-to-1, I just need to show that if I pick two x values, that I'll get two different y values. And that's not hard to do because we know our function now is increasing. So first off, to show 1-to-1, if I have x1 and x2 that are not equal to each other, there's two options. Either x1 is bigger than x2, or x1 is less than x2. I mean, that's basically the only two options because the two numbers aren't equal. And then because it's an increasing function, if we know that x1 is bigger than x2, then f of x1 must be bigger than f of x2, and that's because we're increasing. And similarly, if x1 was less than x2, then f of x1 would also be less than f of x2. Again, that's because our function is increasing. And so either way, regardless, no matter what happens, whether x1 is bigger than x2 or vice versa, we get that f of x1 and f of x2 don't have the same value because one is going to be bigger than the other. So therefore, we are 1-to-1. So we've shown that if we take two different x values and stick them into natural log, we'll get two different y values coming out. Okay, so that was the proof of part 2, and then for part 3, we just needed to show that the function was concave down everywhere, and that's easy enough to show because we knew that the first derivative was 1 over x, in other words, x to the negative 1, so that means the second derivative would be negative 1 x to the negative 2, or negative 1 over x squared. And this is definitely going to be less than 0 for all x's. specifically the x's that are bigger than 0 that we're talking about, but actually for any old x that would also be true, which means f is concave down. And it's concave down for its entire domain. Okay, some other little properties to show. These are ones that you would have shown in pre-calculus, and normally the way you would have done it there would have been starting off by defining things and then switching things to exponential using exponent properties and then going backwards into log properties. We're actually going to do this not using exponential functions at all, because notice we haven't even talked about them existing yet. We haven't proven that an exponential function is even a thing. And in fact, all of these log properties that you know from before, they don't hinge on us knowing that exponential functions exist. In fact, just using our definition of natural log as a definite integral, I can make all of these conclusions. One thing you might be noticing, just as a little side note here, is this one log property, I'm currently restricting it just for rational numbers n. If you're remembering back to your pre-calculus days, your teacher then would have said that this would hold for any old n, not just rational numbers, but irrational ones too. And that is true. The reason we're restricting it to rational numbers just for now is because you're going to see in my proof for number 3, I'm going to use power rule. And up till now, back in chapter 2, we had power rule that was established only for powers that were rational. Later on, we're going to be able to show that the power rule works for any real number, which is lovely. So that means that this property number 3 will eventually be true for any real number n. But for right now, I'm restricting myself just to rational numbers. Okay, so proof of 2, 3, and 4, those take a little bit of time. The proof of part 1 is actually really straightforward. And you might be saying to yourself, wait, how am I going to prove that the natural log of 1 is 0? Well, remember, we know that the natural log of x is our definite integral from 1 to x. And so therefore, natural log of 1 would be a definite integral going from 1 to 1. And one of the things that we had, a much earlier property, this would have been from 4.3, one of the properties for a definite integral is that a definite integral from a to a is always equal to 0. So we're able to prove that natural log of 1 is 0, and that's using, again, our definition of our natural log as a definite integral. Okay, so I'm going to carry on and do my proof of 2, 3, and 4. So they're all kind of similar in the sense in that I'm going to be using derivatives to prove all of them. So first thing for the proof of number 2, I'm going to first look at the derivative with respect to x of natural log of some number times x. And I know that the derivative of natural log should be 1 over whatever its natural log of, and then times derivative of the inside. I'm basically just using chain rule here. So derivative of number times x is whatever that number is. And so I would get 1 over x as my derivative. And same thing I would do here if I were looking at the derivative of natural log of some number plus natural log of x. So natural log of some number, that's a number, and derivative of a number is just going to be 0. Derivative of natural log of x, that should just be 1 over x. And so there we go. I get 1 over x again. This is where we're going to flash back and remind ourselves of something. So 1 over x, and antiderivative for it should be natural log of ax. And 1 over x, an antiderivative of it, should also be natural log of a plus natural log of x. And one thing we know is for antiderivatives, the antiderivatives are all the same. They might be a constant apart from each other, but if you have a function with one antiderivative and another function, a function with a different antiderivative, then the two antiderivatives have to be the same except for maybe plus or minus a constant. So I can conclude, since the antiderivative of 1 over x might be this or might be this, therefore I can say that the natural log of ax plus is equal to the natural log of a plus the natural log of x plus maybe some mystery constant that's the difference between the two of them. So now the next thing is to ask ourselves, well, what is this mystery constant that might be the difference between these two functions? Hopefully it's 0, and then we'll be able to conclude these two things are equal. So good news, we know that the natural log of 1 is 0, so we can say if x is equal to 1, we'll have on the left side natural log of a times 1, which is natural log of a. And on the right side, you'll have natural log of a plus natural log of 1 plus c. We can conclude right away. Natural log of a is equal to natural log of a plus c. In other words, c must be 0. And so therefore, we can make our conclusion that the natural log of something multiplied by something else is natural log of first thing plus natural log of second thing. And that's sort of the similar sort of proof that I'm going to do actually for all of them, for part 2, as well as part 3, as well as part 4. We're all going to start off for all of them basically using a little derivative property, and then making the same sort of argument of saying I have two different things that have the same derivative. They must be the same, different by a constant. Figure out that the constant must be 0, and then therefore we're going to get the conclusion, the thing that we want. Okay, so let's do part 3. So I've done part 2. For part 3, I can do this one right over here and say for myself that we're going to, since we're looking at a to the x to the n and n natural log of x, then basically I'm going to start off with doing the same thing, two little derivatives. One of, what if I had the derivative of natural log of x to the n? And if we're doing this, we can say, of course, chain rule says you'd have, for the natural log part, 1 over whatever its natural log of, and then multiplied by the derivative of the inside. And for that, I would use power rule. And power comes down, power would get reduced by 1. And if I clean things up, a bunch of x's will cancel, and I'll be left with n in the numerator and x in the denominator. Similarly, if I look at the derivative with respect to x of n times natural log of x, then I can say for that one's faster and easier. N is just a constant, it's some rational number, and for natural log of x, its derivative is 1 over x, so we get n times 1 over x, which is n over x. And so therefore we've got two things that have the same derivative, so therefore these two things must be equal, possibly different by a constant. So we're going to make the same kind of conclusion we did in part 2. We'll say natural log of x to the n is equal to n natural log of x plus some mystery constant c. And now, same sort of thing that we did in part 2, we need to figure out that this mystery constant c turns out to be 0. And that's easy enough to do, because if x is 1, then you'd have natural log of 1 to the n, which is natural log of 1, which is 0. You'd have n times natural log of 1, you'd have n times 0, which is 0. In other words, you'd be able to conclude that c must be 0, and so therefore natural log of x to the n is equal to n natural log of x. And therefore we've shown the third of our log properties. Again, the thing to note here is I used power rule, and since power rule only, for now at least, has been shown for rational powers, then that means this log property for now only works for rational powers. But of course we're going to show the power rule for all real numbers soon, so that means we'll be able to make our conclusion that, that this log property works actually for all real numbers. Okay, property number 4, we're going to do much the same thing as we did for number 2. So for that one, I'm going to start off with, again, looking at two little derivatives, showing that they're equal, then coming up with kind of the same sort of conclusion as before. I'll say if I'm looking at the derivative of natural log of some number over x, or sorry, x over some number, that makes my life easier. Number over x makes it worse. Derivative of that would be 1 over whatever is in the inside of the natural log times the derivative of whatever is inside. The derivative of x over a, or in other words, x divided by some number, would just be 1 over whatever the number is. The a's would cancel, and we would be left with just 1 over x. If I were looking for the derivative with respect to x of natural log of x minus natural log of a, again, a is a number, so for natural log of x, its derivative is 1 over x. For natural log of a, that's a number, its derivative is 0. So we have 1 over x again as our derivative. And we make the same conclusion. We have two functions that have the same derivative, so they must be different by at most a constant. In other words, we can say that natural log of x over a is the same thing as natural log of x minus natural log of a plus some mystery constant. And this one is easy enough to do if I were to just put in x is equal to a, because if x is a, you would have natural log of a over a equals natural log of a minus natural log of a plus c. On the left side, natural log of a over a, that's natural log of 1, which is 0. And on the right side, natural log of a minus itself is gone, and then plus constant c is c. So there we go, our constant c is 0 yet again. So now we've shown it natural log of x over a is natural log of x minus natural log of a. And of course, since my choice of letters here is pretty arbitrary, then we can say that if I wanted to use p's and q's, natural log of p and q equals natural log of p plus natural log of q. That would be true as well. So in case you were concerned about my letters not matching the same letters that I actually had in the theorem, that's actually not a problem at all.